So we have this prospective giant graphene deposit / graphite in west central Arizona that we stumbled into by serendipity as a function of a porphyry copper program in a hole that was drilled for porphyry copper ideas and found graphite instead.
That's a piece of the core you're talking about.
Yep. And that black stuff there is graphene-rich graphite.
What is graphene?
What is graphene? Well, you guys have been using graphene without knowing it. It's in what is called pencil lead. And when you scrape the pencil on a piece of paper, you're scraping off little microflakes, and those flakes are graphene. And what they are is it's just for mineralogical curiosity, since we're at the Tucson Gem of Minerals show again. This is the world's first, and it'll take the people that decide whether it's a mineral or not probably 20 years to do anything. Now they'll kill me, but that's beside the point. The world's first two-dimensional mineral. It's a benzene sheet, so that's X and that's Y, and those little rings in there are benzenes that are connected to each other.
No other mineral on the planet has a two-dimensional molecular shape.
Which is one reason you can't X-ray this thing. Well, you can X-ray it if you bomb it from the top, but if you try to X-ray it along, there's not enough dimensionality to get a C-axis out of it.
Oh, wow.
So you get an AB axis, but no C axis, basically.
Okay.
There is some thickness, but it's not enough to produce an X-ray pattern, which is another. Oh well, if it's a mineral, it has to have an X-ray structure. No.
That's the art. That's why it's going to take so long to call it.
You're going to have to get some people to change their habits,
change the rule a little bit.
Yeah, that's hard to do.
2004, it was discovered.
And they got a Nobel Prize for it. And what they did is go back to this simple thing that everybody does now. And this is the field test for it. Go back up. So you take a piece of Scotch tape.
Yeah.
And you find a nice foliation surface with all this black shiny stuff on it. And you put the tape on and then you rip it off like you're trying to remove hair from your leg, like the ladies do. But the point is that you pull a bunch of flakes off. That's called exfoliation.
Okay.
And those tend to be really graphene rich. And that's what you're doing with your pencil, is you're rubbing across a piece of paper and you're flaking it off.
Whoa. These guys figured it out in 2004.
These guys did that with a piece of natural graphite.
Wow.
And then they went through all the natural testing. And most of this is in the, interestingly enough, for those mineralogists out there, all the literature on this is in the material science literature. You won't find Article 1 on this. Well, you might find one in the mineralogy literature, which is very graphene poor. But there is thousands of articles on this thing now because of its material properties.
Wow.
In the material science literature.
Wow. So
you got to go to another part of the library for that.
Graphene is essentially a benzoid hydrocarbon
that occurs in naturally occurring two-dimensional sheets, as we've already noted.
So it's HC. It's kerogen.
No, it's C. However, in those sheets, you can bond the hydrogen atoms to those sheets,
making it an HC system. Pretty
correct,
easy.
And that's why you call it benzene or benzoid, because it's a hydrocarbon sheet. Benzene, the molecule, is just the 1/6 ring guy, but when you punch a bunch of it together, you get a benzoid sheet.
Wow. Add that in.
Yeah.
Interesting.
And depending on how much hydrogen you put in it, in terms of configuring it, you can get, if it's a hydrogenated guy, you get graphene.
Whoa. So it's the hydrogen that makes it either a great capacitor or a great conductor.
And if it's a dehydrogenated guy or a less hydrogenated guy, it's graphene.
It's a conductor.
And that's the world's superconductor. It blows lithium out of the water. This has it's the most conductive material that we know of.
Wow. And the hydrogen.
And graphene, the problem with it is it's so conductive that it's hard to turn it off the conduction.
Can't control the thing.
Well, you could control it by adding a little bit of hydrogen to it.
So it's like a break-in gas system with
Yeah.
graphene,
Yeah.
graphane.
Put a little hydrogen in there, it breaks it.
At the end of where you're taking your energy, stack that up with a bunch of graphane, transfer it on a line, and then it hits the big brake system at the end, and you just got electricity 10 times faster.
Yeah, that's one. That's your engineering argument. I don't know. You're getting out of my tree real quick.
Wow.
When you start going into the electronics
and the other thing
of
is,
this, but
it's the brake system, but it's also a supercapacitor. When you turn it to graphane, which you add a bunch of hydrogens to the thing, it turns it
you
into
can store energy big time.
a major
Store
storage.
electrons.
Comes the COVID.
Try to kill this guy.
Man, it's amazing material. We talk about this. It's semiconductor, semicapacitor, supercapacitor.
Right.
Sneezing, old man. When graphene
Yeah, when triple underline.
is recognized as a new
New
mineral.
mineral, and it should be. It'll be distinguished by the fact that it's the first two-dimensional real.
Wow. And that's why it moves so fast. It doesn't have a third dimension for the electricity to get slowed down to get through its path. It's a two-dimensional path.
Right.
There's no third dimension to the thing. It just
That's
goes
right.
like that.
Right. It's going to go along the plane of the graphene sheet.
Wow. That's amazing.
So to our knowledge, Yellowbird is the first deposit where natural graphene, because they've made it synthesized. Well, there are other places, but this is it's been documented by Raman spectrographic work. We've done a lot of Raman work on this thing. Hey, go back.
This
to
is
that.
where it is. You're done with it. That's the last bullet point, the last word.
No. This is mineralogy stuff.
Ah,
It will be designated as the first type locality for graphene.
that's a prediction?
That's a recommendation.
All right, let's see it. We're going into Yuma King.
So this is actually where Troy was pointing at a little bit earlier on that map. In fact, can you go back to the, I don't think we have a location specific. Where is that gold thing?
This system
Yeah.
right here.
So this is these little blue guys. That's Yellowbird North. That's carbon.
Yep.
And Yellowbird South.
This quartz alkalic deal here, doing the same
Now,
trajectory.
this,
south one.
that guy there, yeah.
The north one is this guy, and then, okay, so we're going into this guy right here.
Yep.
It's got a 155 to 150 age.
Right, because it originally formed as a black shale in a rift basin at the base of what's known as the McCoy Mountains Formation.
Under rifting.
Under a rifting between the Sevier and the Nevada and orogeny. It's in that little pause in there. It's about a 10 million year pause.
Bang, this body of graphene-rich mud packed up in that rifting event.
Yeah, and this actually corresponds with the early opening of the Gulf of Mexico. And there's a lot of hydrocarbon-rich black shales that come in early in that stage. They're source rocks.
So then you bring in the Laramide.
Smackover Formation, for example.
And you bring in the major subduction event after this thing, after it deposits and shapes.
That's right. So, and then so then we have, this is all it's just gunky old black shales. And then we go through a series of metamorphisms, heating metamorphisms associated with thrust thickening, where several generations of thrusts that are added to the top of this thing. And it matures this thing from a normal unmatured black shale up into a graphene-rich black shale. Let's take a look at that. We have some experiment. We'll come back to that in a minute. Keep going, okay. So these are Raman spectra.
Yeah.
So basically you have two Ramans. Let's see, here's the 1250. That's the G peak or the graphite peak.
Okay.
And then there's the D prime peak, which is your conformation of graphene.
Okay.
And what happens is you start out below, you have a big D prime peak. And then as you go all the way up into the amphibolite grades, Sorry, that's the G peak. That disappears. The D peak disappears.
This one.
Yeah.
Yeah.
D prime peak, sorry. Come on down.
So this is
sure about that.
This is your D prime, the first peak.
Yeah.
And it will lose
Actually, that's the D peak. And that's your also a graphene peak.
Okay. And what are you saying along the top here? So this is graphane down here, disordered graphene to ordered graphene.
Right.
To graphite.
Right. So that's a metamorphic sequence there. And this is where our Raman, you can determine a geothermometer from that graphene.
Wow.
This T parameter, which is the R2 parameter, which in part, among other things, depends on the height of these peaks relative to each other. And then people have gone in the Swiss Alps have calibrated classic metamorphic, experimentally constrained assemblages, and that's the temperature versus the R2 ratio.
R2, what does that mean?
Well, that's the ratio of these different peaks, plus that's a linear equation format there.
Oh, it means the R squared?
Yeah, so that's the slope.
So is this top of this pink box the top of this pink box?
Yeah.
Is that what we're looking at?
Yeah.
Got it. So it's cooler where you got a graphane.
That's right.
And then it gets really hot. The metamorphism is just
graphene out at 600 approximately.
Wow.
And then when you get up into the amphibolite grade, that's almost up into the melt window at that point.
Wow. And it fries out the graphane.
Yep. And it goes straight to graphite. There's no D peak. And that is the D2 peak for graphite.
Graphite is not a 2D structured mineral.
Graphite is a 3D. Yeah, it has a C axis.
Wow. Man, that's bizarre. Okay.
So we did we're basically saying we had thrust burial temperatures in the 400 to 550 range.
Right. In the what we're pointing out here in the subsurface and outcrop.
Now, the additional important thing there is there's all those dashed lines are shear fabric associated with the McVeigh thrust, which piled a whole bunch of stuff up here.
Which is causing some action.
Yeah, and it's slicing up our Jurassic porphyry copper system, which is this JA. It's in this JA unit, and it's in skarns on the side of that and some porphyry-style mineralization in the intrusive sequence itself.
This is picking up the shear of this event?
No, that event is 190.
Okay.
And then it gets sliced and diced by the thrust events, which throw all of that thrust fault sandwich over the top of the McCoy Basin. So this is the lowest structural level in the Granite Wedge that we know of.
Wow.
Now, we have drilled through this,
right,
and we've actually gotten down into the green stuff, the JV unit. So we know that it's repeated.
Wow.
Because we did some drilling to play around with this. This is what some of our Raman spectra, we probably have about 100 analyses of different Raman. Not that many, 50. But this basically shows how you do it. So this is the low wave number here and the high wave number here. It's basically light energy that we're playing with here, and you can identify as many mineralogists know, every mineral has its own Raman spectral signature, including graphite, and then now more recently graphene has a very distinctive signature. So here is the D peak.
Yeah, first thing that comes in.
Here's the G peak / band. You can see up in this one here, these are 4 different samples. And up here we have a really well-developed D peak. And we have there's your G peak, and it's got a little shoulder on it. That's not your normal graphite signature. That's saying you've got one of these graphene.
Wow.
interference is going on.
Who's developed the analysis that you're doing right now? Who's developed that? Where's that paper of building the shoulder, and that means graphene and this D peak?
That's in the material science literature. Wow. I have some of that in the PowerPoint, specifically from, I can't remember the name of the author, but I've got that slide. Actually, I don't know if I put that in here or not. I don't think I did. And here's the D prime peak, or the 2D peak. And that's graphene. It's a symmetrical peak. The asymmetrical peak, which you saw in that graphene metamorphic thing, is the graphite, and it's shifted. There's a Raman shift to a higher wave number, about 50 nanometers higher. In other words, that's this shift.
This is now the opposite way, though. We're going from slow.
That's correct, and I was getting a little confused there, but yeah. That's the opposite.
So D, G, and then your double, 2D. Or no. This is, yeah.
Yeah, that's the 2D. Bang. Yeah, that's 2000.
Yeah. Cool.
So wait a minute. So when it starts doing this asymmetrical thing with a shoulder, that's the high temperature graphite signature. When it's symmetrical, like down in here, that's the graphene signal.
Wow.
So we have the graphene signal.
Wow. Okay. Oh, this is the burial history going.
Right. So basically, as we're thrust loading, this is the uncooked.
So you have your deposit, and then you hit this thing 40 million years later, something like that.
Yeah. We have this guy at 150.
Yep.
And then at about 80, we hit it with the thrusting events.
Burial metamorphic event is underway.
Yeah. Cook it. Get up to peak metamorphism, and then as we shear it, that's where the good stuff goes. It's during the retrograde. So this is the graphene perspective window.
Heat it up,
versus
shear it, get your graphane.
Yeah, and the rock, that's what the Raman spectral signals look like.
We're on the edge of this thing from prograde to metamorphic peak.
Yeah.
To retrograde.
Yeah, and we have all of this in a big PowerPoint. Now here you can see how well developed the graphene peak is at the end of the sequence. And here it's pretty well developed. And then here they're about equal. And then down here, they're really not well developed. They're not individuated here. They're just like double peaks. And then it goes to those peaks. And then it goes.
And then you ultimately get somewhere out here where you cooked it off and you have graphite.
Yeah, we never got that far.
Wow. What's up with this shearable event? That's a structural event that's taken us from this over to the retrograde cook.
That's, well, it's what they call in that part of the world, Reynolds and others who did the initial mapping up there, called it their D2 event, superimposed on the D1 event. There's two events of thrusting. There's a southeast directed one, which is typically tied into the so-called severe effect, and that's east-southeast directed. And then that's overprinted in this part of the world by a D2 event, which is southwest or trench directed. That's our flat subduction event coming in.
Rotates. Boom.
Yeah.
Wow.
Flips the, and so we have the two events, and it's during that second event, because that's the biggie, although they're both big, that I think does a lot of the burial metamorphism and creates the shearing on the McVeigh thrust, which is definitely a southwest-directed thrust.
Wow, the second one.
Is the second guy. There's two of them. And then in the middle of the sandwich is the southeast guy, which definitely deforms the Yuma deposit, which is the porphyry guy. So here's... So we knew we had graphene. We knew it had all these electrical properties. Something we got to clean up there. And what's interesting about this is that this is Zong data from Zong Geophysics here in Tucson. And they they did some science for us. Normal IP is sort of half frequency range. They did a full frequency range IP. They kind of developed a extended the MP technology to take a look at this. And here we're looking at the resistivity, and we see this essentially non-resistive layer. That's our graphene deposit.
Wow.
And it's super chargeable, or super high P. High is one of the highest IP rocks I've ever seen. There's another one over here in the upper plate of the McVeigh thrust. The McVeigh thrust is sitting right here. And we've got drill holes, 3 of them here and a 4th one here, and they all kind of hit these really highly. And we've confirmed graphene with the Raman data right there.
Incredibly conductive rock.
Yeah. Well, yeah. It's very conductive.
Which gives it, so it's
in
giving
terms
us a
of
hint.
zero resistivity.
That's right.
Very low resistivity.
So it's transferring that signal with ease.
Right.
Wow.
Yeah, this is some of the highest conductivity that they've ever seen. If we looked at
Is that right?
yeah, they did some petrophysics on the some of the core samples we sent them before we ran the survey, and they were, what the hell is this rock? It's the most chargeable rock we've ever seen, and one of them, and it's the most conductive rock we've ever seen. It's all at the same time, which is telling you you've got both graphene and graphane.
That's right. Oh, man.
And a lot of it.
And then it's a hydrogen game to make it one more or the other.
Yeah, and that's just sort of going on in that zone, yeah. What the actual hydrogen distribution in there is, who the hell knows? But.
Yeah, got to get it out of the ground and look at it. Oh, wait, we did. And we're going to do it. That's what's going to happen. That rock right
show
there.
them that rock.
Here, I'll put it on your camera. I think they'll see it like that. Oh, man.
It's in these black shears. Hold it up to your camera and point at that black side. So that's the retrograde graphene-dominated stuff. And the prograde graphene, you see the nice folding in there? That's also got graphene in it too. But it's early prograde. And the other shear black stuff in the shear fabric is retrograde.
Wow.
Overprinted during the McVeigh thrusting.
That's picking up the 190 event. That's what's those folds and all. That's the age of that.
No.
Okay.
The original black shale rock in here is 150.
Right. The folding.
And then the prograde metamorphism is about, say, 80, 90 to 85. And then the that's D1, and then which is probably that folding event. And then the shearing that's overprinted on that is McVeigh thrust related.
Even younger.
And that's 80.
Got it.
80 to 70, somewhere in there.
Got it. Cool.
Based on everything we know. And there's that rock.
Right. Look at that fold.
So that's probably, well, that may even be a D2 fabric too, as a matter of fact. And so that would be the prograde fabric. And then it's cut by these later retrograde graphite graphene
shears.
That's 2 shear bands.
And that's what we're talking about in La Paz County, that guy right in there.
It's a big deposit. Yeah, there's a lot of it out there.
Wow. The excitement about graphene, because we know it's potentially the answer for renewable future, meaning renewable technology like solar panels, the EV cars. Graphene's actually technically renewable. It can last probably 100 years plus, where current technology you're getting 20 years. So this is why it's very, very interesting.
Well, yeah, one of the fun things to do is to, in the economic realm, is to compare it with the equivalent gold price. Which back when gold, before gold took off at 1,200 gold. And so we're calculating that into what it was per gram at that time. And then, but if you look at
go graphene,
that's $45 a gram.
Wow.
And if you calculate how many grams we have out there of potentially of this stuff, it's up in the trillions, but that's ridiculous. But the biggest problem,
That's right.
big caveat there is right now we've looked at trying to get it out of the rock by just simple flotation processes.
Processing.
Yeah, and we're getting about 10% of it out of the rock right now. But even at the 10% level over a volume like that,
Wow.
make a lot of batteries with it.
Wow. Well, you make fewer batteries. That's the point. We don't need 3 trillion batteries for our electrical vehicles. Maybe we only need
Yeah, you're going to get more bang for your buck. Yeah,
a
maybe
million batteries.
Yeah, I don't know because everything's based on sort of lithium battery right now.
Right. And they're like, how are we going to build all these things? And then, oh, by the way, how do we recycle all this stuff?
And then there's a problem where you're going to get all the lithium because that's not easy to do.
You got a lithium problem. So it's a great story, incredible story that we're going to pay attention to for sure.
Oh yeah, it's potentially the future of what's going on out here.